Let's suppose that I have a box that is at rest. If I apply a force F to that box, and I apply that force over a distance d, then I will have added some energy to that box. The box has started moving, or maybe it's increased in speed, and since I'm applying this force over a distance d, then I have added energy to the box. And we can recognize that because of the increase in speed. I also know that if the force I apply gets bigger, or the distance over which I exert that force gets bigger, then the amount of energy that the box has will be bigger. The way that we define this addition of energy or removal of energy in other cases is through what we call work. If I have a force that acts in the direction of the displacement, the movement of an object, then I am doing work which adds energy to the system, the box. And for an opposite example, if I have a force that acts in the direction opposite the displacement, for example, one that we run into commonly is friction, which would point opposite the direction that the box was moving, if it's moving to the right in this picture, then that frictional force would do work that would slow down the object, that would be removing energy. And so when positive work is done, that increases the energy of the object, and when negative work is done, that is removing energy from the system. And since F, the force, and d, the displacement, are the two factors that seem to be responsible for this, it shouldn't be surprising that the equation for work is equal to force times distance. So I represent work with the letter W, F for force, and d for the displacement of the object. We would quickly find out that if, similar to the picture, if the object is moving to the right, then if I apply a force perpendicular to the direction of the movement, then it's not going to do anything to increase that object's speed. And so really, in our equation, what we should write, a more correct version, would be to say that the work is equal to the force that is parallel to the displacement. And so we're only going to consider the force that is parallel to the direction of the displacement. For example, if I have that same box and I have a rope attached and I'm pulling up with a force F in this direction, which is at some angle above the horizontal, then the force of me pulling, not all of it goes into increasing the speed of the object, only a component of that does. And so if the object is still moving to the right in this picture, the displacement is horizontal to the right there, and it's being just pulled along the floor. If my force F is this force at an angle, then only the force that acts in this horizontal direction would be the force that would be adding or removing energy from that box. And that component is the cosine component of the force F. So this is F cosine theta. And so you'll often see this written, the equation for work, as W equals the force parallel to the displacement, or FD cosine theta. And so this is going to be our working definition of work. If we look at the equation a little bit more closely, we'll see forces are measured in newtons and distances are measured in meters. And so work seems to be measured in newtons times meters. And for that, we define a new unit, which we're going to call a joule. Anytime you are measuring an amount of work that is being calculated, it should be measured in joules. And the same thing goes for energy. Work and energy are closely related. All energies are measured in joules, and work is also measured in joules. Now I'm going to use a kinematic equation that will help us see how work and energy are related. So a while back we learned that the final velocity squared is equal to the initial velocity squared plus twice the acceleration times the displacement. In this example up above, we've been referring to displacement with the letter d, so I'm going to continue to do that. And if I know Newton's second law says F equals ma, then acceleration can be expressed as F divided by m. And so in this kinematic equation, we should see that in the numerator of that second term we have force times distance. And so from the work equation, we know that that is just equal to work. And so the equation looks something like this. And now what I'd like to do is take this equation and solve it for W. And so I'm going to first subtract the initial velocity over to the other side. And then I'm going to multiply both sides by m and divide both sides by 2. And when I do that, then I'm going to get 1/2 m times the final velocity squared minus the initial velocity squared. If we then distribute that 1/2 all the way through, what we get is work is equal to 1/2 mv squared minus 1/2 mv naught squared. And so what this shows us is if we recognize that 1/2 mv squared is the form of the equation for kinetic energy, then what this equation shows us is that work is equal to the final kinetic energy, 1/2 m times the final velocity squared, minus the initial kinetic energy, 1/2 m times the initial velocity squared. And final kinetic energy, kf, minus initial kinetic energy, is just the change in kinetic energy. And so what this tells us is that the amount of work that is done on an object is equal to its change in kinetic energy. And this is a very useful result because it tells us that if we want to change speeds, that is to change our kinetic energy, then we have to do work. Or if we are slowed down by a force, then that results in our kinetic energy changing, then work must have been done on us. And so, in general, in order to change speeds, speed up or slow down, work has to be done. And so we now know that in order to increase or decrease the speed of an object, work needs to be done. That is, the change in kinetic energy is equal to the amount of work that is done. It follows, then, that a change in potential energy, gravitational potential energy, due to an object being raised up or lowered to the ground, should also require that work be done. And so what I want us to imagine is, let's say that we have a book, some object, that has a weight, mg, which points downward. And we're going to take that book and we're going to raise it up a height delta y. And so in the equation, in order to overcome that gravitational force which points downward, we would need to apply a force that is at least equal to mg. And so using our equation here, delta U, the change in gravitational potential energy, is equal to the amount of work that is done on the object in raising it, that amount delta y. The force that I will apply to that object is equal to mg, and the distance over which I've applied it is delta y. And so this equation pretty quickly tells us that the change in gravitational potential energy is equal to mg times the change in the height of the object. What this equation shows us, first of all, is that really only changes in gravitational potential energy are important, because somewhere we have to define the gravitational potential energy as being 0. So if we write out these deltas instead of keeping them all together, what we would have is the final gravitational potential energy minus the initial gravitational potential energy is equal to mg times y final minus y initial. And so what we often do is we will pick the lowest point that the object ever reaches as being the place where h is equal to 0, or the height is equal to 0. And so in my equation down below, I'm going to indicate that the initial y position, which happens here, is going to be equal to 0, and so that will drop out of my equation. And so I'm defining the height, and therefore the gravitational potential energy, to be 0 at that point. And so the equation will just reduce to the gravitational potential energy is equal to mg times the final y position. And so a lot of the times, the way that we've written this is that gravitational potential energy is equal to mgh. And so we are saying that if we define the lowest position as the height equal to 0, and thereby the gravitational potential energy equal to 0, then an object will have a gravitational potential energy of mgh if we raise the object a height h upwards. And so we know that gravitational potential energy is a form of energy that exists due to an object's position in a system. As it's raised up, it has the capacity to be let go of or knocked down, and thereby convert that gravitational potential energy into kinetic energy. And so we say that as it's raised up, it has more and more gravitational potential energy. Another form of potential energy exists in things that are elastic, so things that can be stretched or compressed. And we say that the elastic potential energy is equal to 1/2 kx squared. So UG stands for the potential energy due to the gravitational field, and US stands for the potential energy due to the springiness of an object. And so for an object that is elastic, that obeys Hooke's law, and has a spring constant K, those objects can have an elastic potential energy that's equal to 1/2 K times x squared. And x represents the amount that the object is either stretched or compressed. The greater the stretch distance, the more elastic potential energy there will be. And so if I have a spring, and I stretch that spring by a distance delta x, and that spring has a spring constant k, changes in k or delta x will affect the spring potential energy that is there. And we know for sure that there is energy there, because if I were to compress that spring and then place an object on top of it or next to it and let go of the spring, then the spring would cause that object to go flying in a direction. And so we know that if that object started moving because of the spring, then it must have given it some energy, which therefore means that it must have been storing some energy as elastic potential energy. To summarize, for now we have three forms of energy. We have kinetic energy, which is equal to 1/2 mv squared. We have gravitational potential energy, which is equal to mgh. And we have elastic potential energy, which is equal to 1/2 kx squared. Changes in any one or multiple of these forms of energy will require that work be done on the system, either to increase or decrease any one of those values. And so we could say that the change in kinetic energy plus the change in the gravitational potential energy plus the change in the elastic potential energy must be equal to any work that has been done. And so if none of those values change, then no work has been done on the system. And if only one of those values change, or if one increases then the other decreases, we can still say that the sum of all of those changes in those energies must be equal to the amount of work that's done. And so in general, we will say that the change in the total energy, E, is equal to the amount of work that has been done. Furthermore, we know that we can express the amount of work that is done as the force that is exerted parallel to the displacement, F parallel times D. In most real examples, saying that work is done on the system is practical. because whenever something's moving, there's friction acting on it, and that's going to be removing energy from the system. But in a lot of the problems that we're going to do, we're going to say that the work done is zero, which a lot of the time will mean that something is frictionless. And when we say that, we're saying that the change in energy is equal to zero, or the final energy minus the initial energy equals zero, which means that the final energy is equal to the initial energy. This is also a statement of the law of conservation of energy, which says that energy is conserved. And this is a big deal. Energy is conserved. For anything that is conserved, we can use it to solve problems in which we have an initial and final state, and we're comparing those two states. And so most of the examples we're going to do, we're going to have to think of what type of energy does the object have now, and what type of energy does it have later. We'll equate those two and solve for the thing that we're looking for. Lastly, I'd like to do an example. Suppose we have a boy that is in a building, and there's a window in that building. And he reaches out there, and he takes a ball, and he throws it straight upwards at 10 meters per second. And so this upward arrow represents the velocity of the ball initially. And that ball is going to go all the way up to some maximum height, and then it's going to fall all the way down to the ground. So the ground is down here, and the maximum height is up here. And suppose that I want to know three things. The first thing I want to know is, what is the maximum height? And I'm just going to call that h. The next thing I want to know is I want to know the speed when it reaches the same point where he was reaching out of the window. I want to know the speed at that point. And then I also want to know what is the speed when it gets to the ground. Okay, so three things. The max height, and then the speed at the window, and then lastly the speed at the ground. For the first part, what I want to do is determine the maximum height. And to do this, I want to use conservation of energy. And so for every conservation of energy problem, we need to say when is the initial energy and when is the final energy. They are instances in our problem. And so in this case, the initial energy happens the moment he throws the ball out the window. When that happens, let's say that he is a distance of 20 meters above the ground. If that's the case, then not only does the ball have an upward kinetic energy, but he also has some gravitational potential energy due to being raised up in the building. And so EI equals EF. And for the initial energy, I should write that the ball has kinetic energy, but it also has gravitational potential energy. When the ball reaches its maximum height at the very top here, that ball will momentarily stop before going back down. And so if it stops, then the only type of energy it has at its maximum height is gravitational potential energy. And so if the ball is thrown with an initial velocity v, the kinetic energy is 1/2 mv squared. The initial gravitational potential energy is mgh, and I'll write hi for the initial height. And the final gravitational potential energy is going to be mgh final. And we're looking for that maximum height, which in my equation is h final. First thing I notice is that there's an m in every term of the equation, which will cancel. And so the first term is just 1/2 v squared. The second term, g times the initial height, and on the other side of the equation, g times the final height. Since the initial velocity is 10, 10 squared will give me 100, and 1/2 times 100 is 50. Let's also assume that the gravitational acceleration, g, is just 10 meters per second squared. If that's the case, then the second term is 10 times the initial height of 20, and so that should give us 200. The last term is g, which is 10, times the final height, h. And so the maximum height of the ball is 250 divided by 10, or the final height of the ball is about 25 meters. We have to be a little bit careful about our answer here. Depending on the wording of a question, we may or may not get this correct. So that if we are defining the height in our picture of the ground as being h equals 0, which is the lowest point, then our final answer for this first part says that the ball will be 25 meters above the ground when it hits. And so if the question were to say, how far above the window, then we're already 20 meters off the ground, and our answer should only be 5 meters above the window. For part B, they want to know what is the speed at the window. If energy is conserved, which means that we're not losing any energy as the ball travels up and then travels back down, when the ball gets back to the window and that's at the same point that it was released from, then the velocity of the ball should be the same. All of the kinetic energy of the ball got transferred to gravitational potential energy, and then that gravitational potential energy got converted back into kinetic energy as the ball falls back down. And so we have a decrease in speed as the ball comes up, and then an increase in speed as the ball comes back down. And as long as those two positions are the same, then at that position we should have that the speed is just 10 meters per second, the same speed as when it went up. For the final question, we're asked to find the speed at the ground. And for this part, I'd like to illustrate an important point, and that is we get to decide what the initial and final positions are in our example when we're solving a problem. And so here, I think it may be more convenient to define the initial position as being that of the maximum height, and then the final position being the ground. And so that is a choice that you'll have to make when you solve a problem. If the initial position is the maximum height, then the ball only has gravitational potential energy, and if the final position is the ground, then the ball only has kinetic energy because we defined h equals 0 to be at that point. And so by defining it this way, I don't have as many terms in my equation. And so anytime you can eliminate some of the terms by being clever about which positions you're picking, you should do that. In this case, the initial energy is just mgh, where h is that maximum height of 25. And the final kinetic energy is 1/2 mv squared, where that v represents the v at the ground. Once again, the masses cancel, and I'm left with v equals the square root of 2gh. If g is still equal to 10, and the maximum height was 25, then the speed at the ground is equal to the square root of 2 times 25, which is 50, times 10, which is 500. And the square root of 500 is equal to about 22 meters per second. One last thing that I'd like to point out is that the speed we calculated is greater than the 10 meters per second that the ball had when it was thrown up from the window and even when it came back down, because at that point we are lower in height, and so there has been a chance for more of the gravitational potential energy to get converted into kinetic energy. And so for that reason, since when it reaches the ground, all of its energy is kinetic energy, it's moving at the greatest speed, 22 meters per second.